Hadoop Overview. In this module, we are going to discuss why Hadoop is a good solution for storing and processing large volumes of data. We will also take a look at the history of Hadoop and define at a very high level the Hadoop architecture. We will also look at hardware, operating system, and software considerations for a Hadoop cluster. So, why Hadoop? We know there is more data being generated today from various sources than there was yesterday. And we know that there will be more data generated tomorrow from those same sources than there was today. That data that is being generated has three main characteristics to it. They are volume, velocity, and variety. The volume is pretty simple to understand. How much data is there? How much data needs to be stored? How much data needs to be managed? How much data needs to be analyzed? The velocity comes in two pieces. One of them basically is simply a function of physics. How quickly are we able to write that data to storage? How quickly are we able to retrieve that data from storage? The other factor there is, with respect to velocity, how rapidly is the volume of data increasing? And variety, we have a variety of sources for that data. No longer is it just one or two sources of data, but the sources of data are numerous. Some of the challenges of that big data, although there are many, two significant ones are the amount of time it takes to write and read an amount of data, as well as the type of data it is. Consider 1 terabyte of data stored on one disk. It will take hours to read that 1 terabyte of data, specifically about 2.5 to 3 hours. Now, we can certainly make that faster by taking that same data and spreading it across 100 or so smaller disks and then doing those reads in parallel, which we're going to talk about a little bit later. Another challenge of big data is the fact that the data that is generated today in many cases no longer fits into the traditional relational model that we are so familiar with. This is a challenge that also has a benefit, and that is if we have unstructured data, one can look at that data from many different angles, ask many different questions of that same data. Where does all the data come from? What are the sources of that data? We're familiar with many of them. The social media data, for example, Facebook and Yahoo. Also sensor data. Every jet engine on every airplane flying generates a huge volume of data for every hour that airplane flies. We know there is tremendous amounts of email as well as text messaging data and many other sources of data. One thing that's true of all data is that there is value in that data. The value is dependent upon one's business. Those customers that capture, store, and evaluate data are trying to extract value from that data with which they can make solid business decisions. Let's take a look at a couple of traditional computing environments and their strengths as well as the challenges that large volumes of data imparts upon them. The monolithic computing model typically consisted of many powerful, fast CPUs that worked quite well on relatively small amounts of data. As the volumes of data increased, the solution to this challenge was simply build a bigger and a faster computer with more CPUs and more memory. Of course, the biggest challenge with this model was the fact that it was very, very expensive to build a brand new, bigger supercomputer simply to handle the larger volumes of data. Admiral Grace Hopper, acknowledged as a pioneer in distributed computing model, suggested by historical reference that just simply building a larger computer in a monolithic environment was not effective nor sufficient enough to accomplish a task. The concept of distributed computing suggested processing be distributed across a cluster of machines, or multiple nodes, if you will. This is primarily focused on distributing the processing workload across many powerful computers. The data itself would be stored remotely on a separate storage appliance. And typically there are several frameworks that exist to support such an infrastructure. Distributed computing, as good as it is, also has some challenges in that it did not and still does not scale gracefully. The data stored remotely must be copied to be processed. Again, the time to read that data, which can take hours and hours, must be accomplished before any of the processing can begin. Then the problem becomes more of a challenge as more nodes are added onto the cluster. Hardware failure is a significant consideration. Distributing data means that failure of any part of the system could conceivably corrupt some of the data. And though replication is a solution, it takes time and more storage and overhead to replicate that data. Sorting, combining, analyzing data from multiple systems is a challenge because the fact that multiple systems talk different languages and those interfaces have to be generated in order to allow them to work together. Is Hadoop the solution for big data challenges? Before we look at the core Hadoop solution, let's take a look at some of the characteristics of a big data model and what they might be. In our big data model, which is going to consist of many nodes of hardware, failure is going to occur. So when it does, let's have a set of characteristics that allow that failure to be handled efficiently. Among those characteristics or properties is automatic failover. In other words, any job is going to complete automatically regardless of what is going on in the system around it. And when a failed task occurs, that task should be restarted transparently. In other words, nobody should have any manual intervention in the system to get any given task to start again. If I have a cluster that has 10 nodes and I lose one of those nodes, then the loss of capacity should be no more, in this case, than 1/10 of my total cluster size. If I have the loss of a node and it results in 25% of my capacity lost, then something is wrong with the definition of my cluster. Restoration of failed components, okay, does restore lost capacity. In other words, I don't have to rebuild if I lose a component. All I have to do is fix that component and have it rejoin the cluster. The situation should be a recoverable one. And I should have consistency of the data. In other words, the system should ensure that data is never corrupt and that we do not get partial and or invalid results for any job that is running in our cluster. With horizontal scalability, jobs running in relative isolation from one another, simple programming model and failure characteristics all in mind, let's take a look at core Hadoop and see how it attends to those characteristics. Core Hadoop consists of two main components, a distributed file system referred to as HDFS and a flexible analysis engine referred to as MapReduce. HDFS is a shared distributed storage environment for large data files and has a potential for redundancy for purposes of reliability and the availability of data. MapReduce abstracts the processes of writing to and reading data from files stored in HDFS. It breaks raw data into basically key and value pairs for tailored processing requirements. In addition to the two main components, HDFS and MapReduce, Hadoop consists of an infrastructure to make all the components, of course, work together, consisting of a web interface, monitoring, scheduling tools, as well as a variety of file system utilities. The distributed computing model we spoke of earlier typically requires some very complex synchronization code be written into the system, as well as typically expensive high-end fault-tolerant hardware and redundant high-performance storage appliances, since the data is stored remotely to the compute modules. Hadoop just takes a much different approach than this. The Hadoop approach is based on a couple of white papers, HDFS and MapReduce, that were put out by Google in the 90s, and it addresses these problems that you would find implicitly in a distributed system. Hadoop's goal is to simply achieve linear horizontal scalability, okay, with minimal chatter between the nodes like you might get in a shared nothing environment, but to be able to scale horizontally by adding new nodes to increase capacity or performance, and be able to add these new nodes both simply and cost effectively. Okay. Recognizing that components in a cluster will fail, you got to make sure that you provision using widely available commodity hardware and provision what you currently need and scale out at that point in time where scaling out becomes necessary. Data access is a bottleneck. Okay, moving data from a storage appliance in the traditional distributed computing model to the processors is very time consuming. Copying lots of data over the network takes large volumes of time as well as network bandwidth. The idea of Hadoop is to store data and process that same data on the same machines in the same cluster. This will eliminate any need to copy that data between the nodes, eliminate much of the network bandwidth challenges one might run into when copying large volumes of data from an external storage devices. And then process that data intelligently with what is referred to as data locality. Bring the data itself to the compute engine, okay, that it is stored generally next to. Okay. process that data on the same node as it's stored on if it is humanly possible to do so. Disk performance is a bottleneck as well, okay? Although the ability to capture and store more data on disk has increased over the years, the performance of the disk itself has not been able to keep up with the ability to capture and store more data. So capacity has increased, scan performance, while increasing somewhat, has not scaled as well as capacity has. A simple example, assuming one disk and 3 terabytes of data and a transfer rate of roughly 300 megabytes per second, okay? Little over 2.5 hours to read the 3 terabyte file, okay? If we take that same 3 terabyte file, break it up and spread it across 1,000 disks, okay, then it will take roughly less than 10 seconds to read that same 3 terabyte file. So divide and conquer is the primary watchword, if you will, of a Hadoop cluster. Code for distributed computing is complex, requiring a lot of synchronization code, a lot of networking code, a lot of file I/O code. Okay? Hadoop's infrastructure will abstract all of the complex coding requirements away from the developers. It is all part of the infrastructure, which the nice part about this is the MapReduce developer, when he or she is asked to create a MapReduce job, focuses on writing a job that answers a question that brings value to the business. He or she no longer is required to worry about having to write synchronization code, network code, I/O code, anything along those lines. Typically, the mappers and reducers for a MapReduce job will be written in Java. However, Hadoop streaming is supported and does allow for mappers and reducers to be written in other languages as well. Distributed systems take advantage of very expensive components. Typically they are high-end carrier class equipment with redundancy built in. The Hadoop concept basically is failure is inevitable. So plan for it. Make it a part of your replacement strategies. Minimize the effect of any failure that occurs, and Hadoop will do this for you very, very well. Okay? Machine failure is a common and oftentimes regular occurrence, as you can see. If we have servers in our cluster that have a mean time before failure of 5 years, which is just short of 2,000 days or so, if I have a 2,000 node cluster, I am going to lose roughly 1 node per day. Okay, so the loss of a node should not be a surprise. It should be something that we expect, something that we have provisioned for, something that we have a strategy for replacing with the minimal amount of interference with our cluster activities. The history of Hadoop. Prior to Hadoop, there was an open source web search engine named Nutch that was created by Doug Cutting and Mike Caffarella in about 2002. In 2003 and 2004, Google released both the Google FileSystem and MapReduce white papers. In 2005, Doug Cutting was tasked with re-architecting the Nutch project. Out of the Nutch project in 2006 factored Hadoop as a sub-project. Later, Hadoop became a top-level Apache project around 2008. A very, very large amount of the early development of Hadoop was led by Yahoo. Today, Hadoop is pretty much mainstream. Many ecosystem projects have been spawned. Most of these ecosystem projects are in fact Apache top-level projects, and they include ecosystem tools to allow one to work within the Hadoop environment. They are known as Hive, Pig, Oozie, Flume, HBase, and there are many, many others. Many organizations have migrated to Hadoop, have increased the focus on enterprise-level features and tools. Keep in mind, Hadoop is evolving and does change very, very frequently as an open source product. Hadoop versioning is somewhat chaotic. MapReduce all by itself demonstrates this as well, in that there are two Java APIs, and they are referred to commonly as the old API and the new API. In addition to two separate APIs, there are also two task management systems. One is referred to as Classic MapReduce, or MapReduce version 1.0, or MRV1 as it's called, and the other is MapReduce version 2, or MRV2, also referred to as YARN, an acronym for yet another resource negotiator. Hadoop architecture. Hadoop uses a master and slave topology. Master nodes include what is referred to as the name node, which maintains all the metadata for the cluster, a checkpoint node, which performs checkpoint operations on behalf of the name node, a job tracker or resource manager, which manages task assignments, a high availability name node if one is required, and federated name nodes. The slave nodes include data nodes, which is the storage device, stores HDFS files, manages the reads and the write requests for those files, and task trackers or node managers, which perform map-reduce tasks. As you can see on this slide, the name node daemon runs in its own JVM on the name node master. The checkpoint node daemon runs in its own JVM on the checkpoint name node master. And of course, the resource manager daemon runs in its own JVM on the resource manager master. And that the data node daemon runs on each and every one of the data nodes in its own JVM. And the running of these daemons in its own JVM accounts for the isolation that is referred to earlier on in the slides, such that if any one daemon were to fail, it is totally isolated from all other daemons in the system and should have no effect on any other jobs that might be running in your cluster. Hardware considerations for a Hadoop cluster. Scaling your cluster is relatively simple, which means you can start with a moderate-sized cluster, one that satisfies your business requirements, and then grow that cluster as your business requirements change. However, you do want to make sure you do have a scaling strategy, because as simple and easy as scaling is, there is an overhead with respect to time and resources that are required when scaling your cluster. Okay? You don't want to be adding new nodes each and every week. Typically, the amount of data one has defines the initial size of the cluster, plus some kind of a factor defined by the rate or the volume in which your data is going to increase over time. Typically, storage requirements are the determining factor for when you want to grow your cluster. However, after you've gained a significant amount of data and information about how your cluster is used, sometimes processing requirements and or memory requirements can be other reasons that you might want to or need to grow your cluster. Storage requirements do drive cluster growth typically. Data volume, if it does so increase at the rate of about 1 terabyte a week, means that 3 terabytes of storage are going to be required to store the data alone because of the block replication factor. Also, there is additional overhead. Not all 3 terabytes of storage is available to HDFS. Typically, there's a 30% overhead that is utilized for temporary files, etc., that are written to local disk. So, for example, if a data node incorporates 4 1 terabyte drives, then you're going to need 1 new node per week. Okay, over a 2-year period of roughly 100 terabytes of growth, it's going to require about 100 new nodes. The important part here is have a plan for scaling, have a mechanism by which you can anticipate when you will have to scale. Also important in your cluster design are your workload considerations. Workloads typically fall into 2 or 3 different categories: balanced workloads, compute-intensive workloads, or I/O-intensive workloads. Balanced workloads are those whose jobs are typically distributed across a variety of different job types: CPU bound types, or disk I/O bound types, or network I/O bound types. There are also compute intensive workloads. Those typically tend to be the deep data analytics processes. They typically require a significant amount of CPU cycles, so large numbers of CPUs are required, and probably higher frequency CPUs. Typically, large amounts of memory to store the in-process data is also required. I/O intensive workloads, however, or sorting type workloads, just require more disks, not necessarily more processing capacity, but more disks per node. Okay? If one is uncertain what type of workloads they're going to have, I think the best way to do this is to err on the safe side and set up a cluster that favors balanced workloads. Remember that we talked about earlier, things are going to break, okay? And this is a core premise of Hadoop. Okay? Disk failures are going to break. The infrastructure must accommodate any disk failure that occurs. Task failures should be managed by the job tracker or resource manager. Data node failures must be managed by the name node. And again, the infrastructure of Hadoop will manage each and every one of these different failure scenarios. Master nodes, the name node, the standby name node, the secondary name node or checkpoint node, the resource manager or job tracker nodes. All of these typically are single points of failure. That means, for example, if the name node goes down, then the accessibility of any of the metadata is unavailable, which means none of the data on your data nodes is accessible. If a job tracker or a resource manager node goes down, then no jobs can be run on the cluster. Okay? Any jobs that are in flight, if the job tracker or resource manager goes down, will terminate at that moment in time. Slave nodes, since you will have many of them, should be commodity hardware. The adage is typically buy more slaves, not more expensive slaves. Okay? Since they are going to fail, buy inexpensive, not cheap, but inexpensive slaves. Okay? Workload patterns and cluster size define CPU choices typically. Small clusters, 50 nodes or less, quad-core, medium clock speed CPUs is more than sufficient. Once your cluster gets beyond the 50 nodes or so, then maybe dual quad or maybe even dual hex-core CPUs. Again, medium clock speed would again be sufficient. If you have a data analytics intensive cluster, then maybe you might want to increase the clock speeds on those CPUs. Lot of memory. Okay, a lot of memory is required, whether it be a master node or a data node. Okay, a map task and or a reduce task, either one is going to consume between 1 and 2 gigabytes of memory typically. Okay, The number of tasks that can run on a given node is typically 1.5 times the number of CPU cores. Okay? So if I have a dual quad-core CPU, that means that I can run roughly 10 tasks on that node. If each task requires a minimum of 2 gigabytes of space, for example, I need to have at least 20 gigabytes of memory. Again, plus memory for the operating system, plus memory for the data node daemon, plus any other daemons that might be running on that node as well. So 24 gigabytes is probably minimal amount of memory on any given data node. 48 is better, 64 is probably ideal. On your slave nodes, the more drives, typically the better. 4 to 12 drives of the 1 to 2 terabyte capacity is pretty much the standard, if you will. Okay, 3 terabyte drives do work. However, if a node fails or if a drive fails and data needs to be copied from node to node, that could throw a lot, 3 terabytes of data onto your network and impact network bandwidth capabilities. Okay. Traditional 7200 RPM SATA drives are sufficient. If you want to spend a little bit more money, then slightly above average MTBFs might be an advantage. Traditionally, it's going to be the drives that are going to fail most frequently in your Hadoop cluster. The drives are configured in just a bunch of disks array. RAID is slow, not necessary, not required, simply due to block replication. So just a JBOD configuration, just a bunch of disks is more than sufficient. More smaller disks is preferred over a few larger disks. And the reason for that is for, of course, increased parallelism. The master nodes, typically single point of failure, typically want to be a higher quality than your data nodes are. They typically want to be carrier class hardware. They want redundant everythings if possible. Redundant power supplies, dual Ethernet cards, bonded where possible. Okay. Large number of CPU cores, 16 to 24 cores on the name node, and the checkpoint node is ideal since the name nodes and their clients do have a lot of messaging going back between them. You need more cores to handle all of this messaging traffic. They don't have to be fast. Medium clock speeds should be more than sufficient for your master nodes. Memory requirements on the name node is critical. Okay, all of the metadata that references all of the data stored on your data nodes is stored in memory on the name nodes. Okay. The more data that you store on the name nodes, the more memory is utilized on the name node. As far as storage requirements, disk storage requirements on the name node is concerned, you do want RAID storage on the name node. You typically want 4 redundant volumes. You want some of those volumes local to the name node, some of them networked, and they want probably be 1 terabyte volumes, but don't need to be any larger. The job tracker resource manager nodes do not require RAID storage, as most of the state of those devices is saved to HDFS and stored on disk. Master node recommendations: use the same specifications for your name node, for the checkpoint name node, and for the job tracker resource manager node. Okay, this gives you an alternative to any one of those nodes failing. You always have a device that you can swap in at the last second. Okay, the job tracker and the resource manager can run on a data node if you want to run them. It's risky, does not and is not recommended, does require significantly greater amounts of memory to be installed on that data node. Should always encourage high availability name nodes. High availability name node is a name node that runs in an active passive environment. And federated name nodes should be considered when applicable. We will talk later in this course about high availability name nodes as well as federation. Operating systems and software considerations for a Hadoop cluster. The choice of operating system for your cluster is up to you. The recommendation typically is to choose an operating system that you are comfortable with and familiar with based on your experience and resources of the administrative team. Traditionally, Red Hat Linux seems to be a real good choice for the masters, and it does come with a support contract. CentOS is a good choice for your slaves. Doesn't have a support contract with it, but the price is certainly right. Okay? If you have a team experienced in SUSE or Ubuntu and Fedora, use those resources and use those operating systems as well, keeping in mind the strengths and weaknesses of each of them. The same advice applies to file systems. Which one do you choose? Choose the one that you're most comfortable and familiar with. If you have a team with a lot of experience with ext3, then stick with it unless there is a good reason that provides value to change. Okay? ext3 is traditionally the most common OS and file system use. ext4 becoming more and more common as time goes on. XFS used quite often, does have its strengths, does have its weaknesses. Again, choose the file system that you are most familiar with and that your admin resources are most familiar with as well. Which JVM do you want to use? The one that says Sun on it is the one that is supported. So you want to use the Oracle or Sun Java environment. Go to java.com to download it. 1.6 or higher is required by Hadoop. Hadoop builds and does run on OpenJDK. It is not bad for development environments. It is good for debugging purposes. Hadoop also has been run on the JRocket JVM, which is not all that different than the Sun JVM, but it does manage heap and memory differently. Never have seen it used on a production scale cluster. Hadoop 20.2 does work with IBM Java 6 Release 8 for those who might be running in that environment.